Okay, today we are going to discuss about transition element property. So, just we are discussing about the properties of the transition element one by one. And today our topic is magnetic properties. Okay, if you are taking each elements, okay, each element has, if I am taking each element has some magnetic properties. That is, element has some magnetic properties. This is usual. So when you are, if you are taking any element, just in the presence of, just if you are applying a magnetic field, in presence of magnetic field, there are two types of magnetic behaviors are observed. One is paramagnetism and second one is diamagnetism. Okay, in addition to that, we are going to discuss a ferromagnetism also. So first one, what is paramagnetism? This paramagnetism, this substance are attracted by the magnetic field, that is strongly attracted by the magnetic field. There is one point. So what are paramagnetic substance? Definitely that ions or substance that are strongly attracted by the magnetic field. And this second one, this should have a unpaired electron. Should have a unpaired electron. For example, for this paramagnetism exhibited ions, you will take example, you will take a Cu2 plus ion, paramagnetism character. And if I am taking Mn plus 2 paramagnetism, if I am taking Mn plus 3 also paramagnetism, like that. The example for the paramagnetism character. And what is diamagnetism? This diamagnetic substance are repelled by the, they are repelled by the magnetic field. They are repelled by the magnetic field, and this diamagnetic substance, these are paired electron in the orbital. We should have a paired electron. And example for this diamagnetic substance, you will take scandium 3 plus, copper plus, like that, zinc plus 2 ions. Okay. So mainly we are discussing about paramagnetism and diamagnetism. In addition to that, one more property, that is ferromagnetic substance. So what are ferromagnetic substance means? These substances are strongly attracted by the magnetic field, that is strongly attracted by magnetic field compared with paramagnetic. Okay, and one more thing, this magnetic behavior should be retained even after the field is removed. Okay, the magnetic behavior should be retained after the field is removed. after the field is removed. And example for this ferromagnetic substance, we will take a common example, iron, copper and a nickel element. These are strongly attracted by the magnetic field. Okay, so three magnetic behaviors. One is paramagnetism, diamagnetism and ferromagnetism. Next, if I am considering an electron of atom, okay, just an electron of atom as two types of behavior. One is the electron, how it is that is rotating in the orbital. The rotation of that is nothing but the motion of the electron. That is motion of electron. Okay, motion of electron. So if I am taking an electron, it will be spin about its own axis, one thing, that is spin about its own axis and the spin around the nucleus. Around the nucleus. So far we are giving that spin about its own axis, that is given by spin quantum number. Okay, and spin around the nucleus, that is given by orbital quantum number. Quantum number. Okay. So if I am taking orbital, like any orbital, suppose if we are talking about a transition element, just we will take a d orbital. Okay. If I am taking only one electron in the first orbit, this one electron create a magnetic field about its axis. Okay, and this is moving in one direction. Suppose if you are considering one more the d orbital, like containing d6 configuration. You take d6, a d1 configuration. So d6 means one more electron present in the same orbital. Okay. So here only one electron, so creates a magnetic field around it. And here also first electron creates a magnetic field that is moving in one direction. And second electron, antiparallel electron, creates a magnetic field that is moving in opposite direction. So that the magnetic moment is taken as 0. Magnetic moment is 0. Okay, so that one spin will be cancelled by the another spin. But here we will have a magnetic moment. And from that we will come to one point, whether the transition element, all the element in its ion state, if you have at least one unpaired electron in the d orbital, you may calculate the magnetic moment. Suppose if all the electrons are paired in the d orbital, like suppose if all the electrons are paired like this, there is no magnetic moment. Okay, there is no magnetic moment. The magnetic moment value is 0. So if you are taking an electron, there are two things we have to remember. One is spin about its own axis and spin around the nucleus, and based on that we are discussing about the magnetic moment. Okay, so from that, what is magnetic moment? How can you calculate the magnetic moment? So the magnetic moment value can be calculated by the formula root of n into n plus 2 Bohr magnetons. That is, the magnetic moment value can be given by the formula mu is equal to root of n into n plus 2 Bohr magneton. It is a formula, and where n represents number of unpaired electron. What does n represent? Number of unpaired electron. So by using of this formula, you can calculate how many number of unpaired electron in a species, or you can calculate by using of unpaired electron you can calculate the magnetic moment value. Okay, next we are going to see how can you calculate the magnetic moment for different ions. Let me take some example for ions. Okay, I will give you configuration. From that configurations, let me take how to calculate number of unpaired electron, and from that we will calculate the magnetic moment value. Okay. So first let me move D0 configuration like that. So I will give you first ion scandium plus 3. Scandium plus 3. We know scandium is what? Actually scandium is outer electronic configuration 3d1 4s2. 3d1 4s2. The d orbital, how many electron? Only one, s left 2 electrons. Okay. So if I want to calculate for scandium 3 plus, okay, removal of 2 electron, removal of 1 electron, so 3d0. So the d orbital is fully empty. There is no electron present. So from that we comes to know the number of unpaired electron here is 0. If the number of unpaired electron is 0 means the magnetic moment value also 0. Okay, that is scandium. Not for scandium 3 plus, if I am taking Zn 2 plus, like titanium 4 plus, all 0 complex, 0 magnetic moment complex. Okay, like one example I have mentioned. And next, if I am taking titanium plus 3 complex, titanium plus 3 complex, generally titanium means we will get 3d2 4s2, 3d2 4s2. For titanium 3 plus you will get only 3d1, that means the d orbital contain only 1 electron. So even if you have only one unpaired electron also, that contributes a magnetic moment value. So how many number of unpaired electron? Only 1. So how can you calculate magnetic moment? So magnetic moment mu is equal to root of number of unpaired electron 1. Okay, so number of unpaired electron only 1. That is, you can substitute from this value of formula 1 into 1 plus 2. So totally you will get here 1 plus n is number of unpaired electron 1 plus 2. Okay, so you will get 3. So the value was root 3. Root 3 value is 1.73. So the magnetic moment you will get 1.73. And same if I am moving with one more ion, titanium, next you will take vanadium 3 plus complex. Okay, and for vanadium you will get a electronic configuration 3d3 4s2. For vanadium you will get a electronic configuration 3d3 4s2. So vanadium 3 plus, it gives only 2 electrons removed, here 1 electron removed. So 3d2. How many electron? Only 2 electron. So if I am taking 2 electron means unpaired electron 2. So number of unpaired electron I can put 2 here. So magnetic moment value mu is equal to, substitute n is 2. So 2 into 2 plus 2. So it comes root 8. So the value is 2.83 magnetic moment. Okay, and next we have to take titanium. Next is for chromium you can take. If you want to take chromium, so chromium in different oxidation state. So chromium, the outer electronic configurations, if I am taking chromium plus 3, you will take for generally chromium is what, in order to write 3d4 4s2, we will write 3d5 4s1 like that, 4s1. Okay, you want to get the chromium unpaired electron. Now I am talking about unpaired electron 3. For that, I'll remove a 3 electron. So chromium plus 3, you will get removal of 3 electron, 3d3. And the possible number of unpaired electron, 3. So you will get paired electron, 3 means we can calculate magnetic moment. Mu is equal to, okay, so I can substitute unpaired electron 3 plus 2. So it gives root 15, that means 3.87 magnetic moment. Okay, and we can calculate for Mn plus 3. So usually Mn means we'll get the electronic configuration 3d5 4s2. For manganese plus 3, we have to remove 3 electrons. So here 2, here 1. So we'll get only 3d4. So 3d4 means number of unpaired electron, we have only 4. So if I substitute 4, number of unpaired electron, magnetic moment value will be 4 plus 2. Okay, so that gives root 24, the value is 4.89 Bm, that is Bohr magneton. And next we are going to calculate the same type of calculations for the complex ion Mn plus 2. In Mn plus 2, there are the D configuration and the number of unpaired electron, and from that we are going to calculate the magnetic moment value. Okay, so for Mn2 plus, the configuration I can write for Mn as 3d 5 4s2. For Mn plus 2, you will get 3d5. Totally the number of unpaired electron, totally 5 unpaired electron. So where n is what? 5. The magnetic moment value I can give you root of, okay, 5 into 5 plus 2. So that gives root 35. Okay, root 35 value will get 5.90 Bm. That is Bohr magneton. Okay, and next along with that manganese, next we are going to calculate for a Fe plus 2 ion. So manganese, iron, copper, nickel, like that. So if I am taking iron, iron is usual configuration 3d6 4s2. For iron plus 2, you will get only 3d6 configuration. That 3d6 configuration, you will get only the number of electron. Here I can show like this, and the number of unpaired electron only 4. That gives a magnetic moment. 4 means 4 number of unpaired electron, 4 plus 2, that is, okay, here 6, 24. So 24 means you will get the 4.89 Bohr magneton value. Okay, and next complex we will take cobalt complex. Okay, for cobalt plus 2, you take cobalt atom, you get 3d7 4s2 configuration. CO plus 2 means we have to remove this 2 electrons, so 3d7 only possible. So d7 means how many number of unpaired electron calculated? 3d7. So 1, 2, 3, 4, 5, 6, 7. Here the calculated unpaired electron is only 3. So I can substitute 3. So if I am taking mu is equal to root of, that is 3 into 3 plus 2. So that gives root 15 value. So root 15 you will get 3.87 Bohr magneton. And same way for nickel, copper, zinc we can calculate. For nickel 2 plus, so nickel ion is 3d8 4s2. Nickel 2 plus means only 3d8 configuration. So 3d8 means I can show the d orbital filling 1, 2, 3, 4, 5, 6, 7, 8. Number of unpaired electron only 2. So calculated magnetic moment root of 2 into 2 plus 2. So root 8. So root 8 value will get 2.83 m. Okay, and the same way copper, that is Cu plus 2. If you want to calculate for Cu plus 2, generally Cu is what? Just we are taking copper 3d10 4s1 outer electronic configuration. For Cu plus 2, here remove one electron, here remove one electron, so 3d9. So the 9 electron will be arranged in the d orbital. 1, 2, 3, 4, 5, 6, 7, 8, 9. So number of unpaired electron only 1. So only 1. So mu is equal to the number of unpaired electron 1 into 1 plus 2. So the value for root of 3 is 1.73 both magneton. In the same way, the last zinc, if you are calculating Zn2 plus. So usual zinc outer electronic configuration 3d10 4s2. Just if I am removing the 2 electron from the zinc, you will get only 3d10. That means 3d10, the d orbital, how many electron? 4, 5, 6, 7, 8, 9, 10. The number of unpaired electron is 0. So the mu value also 0. So here I have shown that how to calculate magnetic moment. If you know the number of unpaired electron, I have given that number of unpaired electron starting from 0, 1, 2, 3, 4, 5 and again decreasing number of unpaired electron 4, 3, 2, 1, 0 for some of the ions I have shown. And from that you can calculate the number of unpaired electron, whether a compound is colored, how many unpaired electron. Based on that you can calculate the magnetic moment. Next we are going to see the formation of colored ions. If I am taking some metals, okay, forms a color in their aqueous solution in the presence of the visible light. So in the transition element, some of the metal ions exhibit color. But how this color will be exhibited, that can be explained based on the excitement of, that is excitation of electron from the ground state to excitement of electron from the ground state to excited state. So if I am taking the d orbital totally 5 orientations, 5d orbital. So in the 5d orbitals, okay, in the presence of a crystal field effect, in the presence of crystal field effect, okay, the d orbital split into 2 energy level. One is a T2G level and another one is a EG level. The T2G energy level is low energy level and the EG energy level is high. Okay. While the excitation of the electron from the low energy level to high energy level is not taken as it is. Yeah, that is, to excite the electron from the low to the high, there must be absorption of some light energy. And that too, that light energy is obtained from the visible region. So what type of light, that is the frequency of light absorbed, that is the frequency of light absorbed depends upon the nature of a ligand. Depends on nature of a ligand. Okay, in the formation of complex, we should concentrate about the nature of a ligand. Ligand weak field is strong field, and based on that we have to select the frequency of a light that should be absorbed, because absorption of light only can generate the movement of the electron from the lower energy level to the higher energy level. Okay, and like this I am going to take one example and I will explain what is color formed. Okay, so if I am taking titanium complex, that is titanium H2O 6 3 plus complex. Okay, if I am taking titanium H2O 6 3 plus complex. Okay, yeah, the titanium, the oxidation state I can calculate, because water is a neutral ligand, so no problem with the 6 number. So titanium is in the oxidation state of a +3. So I will take, if I am calculating X here, neutral ligand, so X plus 0 equal to charge on the complex will be +3. So we will get X is equal to +3. The titanium in the oxidation state of a +3 level, that is +3 oxidation state. Okay, so usually titanium means just we are taking a outer electronic configuration for titanium 3d2 4s2, that is the number of electron in the d orbital will be 2, the number of electron in the s orbital will be 2. So I can give you that is 3d orbital like this, 2 electron, and the s orbital will be 2 electron. If I am taking titanium +3, okay, so we have to remove 3 electron, 2 from S, 1 from D. So 3D, 1. So we'll get the number of D electron is only 1. And S is completely 0. Okay, so titanium +3 has how many unpaired electron in the D orbital, means only one single electron. So in the presence of a crystal field effect, this titanium d orbital, okay, d orbital will be split up into, that is this d orbital, okay, this 3d1, this orbital split up into 2 energy level. Okay, one is T2g orbital and another one is EG orbital. Okay, one is T2g orbital lower energy and another one is EG orbital higher energy. Now what happened here? How many electron in totally d orbital? Only 1. So that d electron will be present in the first orbit, that is in the lower energy. So in the presence of a crystal field effect, okay, thus we are split up d orbital into 2 different sets of d orbital. Okay, now this electron absorbs energy, okay, from the visible light. This absorption of energy from the visible light, that too absorption of a yellow light. Absorption of yellow light, okay, that one electron will be excited to this orbital. Okay, absorption of a yellow light, the single electron, it is excited to the higher EG orbital. Okay, so while during that excitation, some of the red color and blue color also will be transmitted. And because of that combination of a red and blue color, the titanium +3 complex, the titanium +3 complex will be appear as purple in color. Purple in color. So if you want to show the color of the complex formed by the metal ion from the d block element, definitely it should have a unpaired electron. Even one unpaired electron contributes the color of the complex ion. This is a first example. And if I am taking any that is Zn2 plus ion, okay, Zn2 plus. Usually Zn is what? 3d 10 4s2, that is 3d 10 So number of unpaired electron is here we have to calculate. So here number of unpaired electron is 0 because all the 5d orbital are completely filled for the Zn2 plus. Okay, so Zn has 3d10, 4s2. Zn2 plus the d orbital contain how many unpaired electron? 0 unpaired electron. So Zn2 plus is colorless compound, colorless ion. Okay. In the same way, if I am calculating for copper, but generally copper plus ion. So generally copper is what? 3d10, 4s1. Okay. So if I am calculating Cu plus, so you will get only this 3d10. Again 3d10 means the number of unpaired electron not possible. So the ion is colorless. 3d10. In the same way, similar, if I am taking Cu2 plus, the general configuration 3d10, 4s, 1. Okay, so for copper 2 plus, there are totally number of electrons 3d9. So 3d9 means I can represent electron here 5, 6, 7, 8, 9. So 1 unpaired electron. So this ion is colored complex. The color of the ion is blue in color, and the Cu plus colorless, and the zinc also colorless. Okay, so from this formation of a colored ion, how this color will be formed? Color will be attributed to the different ion means they are given the point as excitation of the electron from the ground state to the excited state. Only if the electron available for the excitation, then only you can excite the electron. And strictly if you follow that, then the presence of an unpaired electron contributes the color of the complex. If the number of unpaired electron increases, magnetic moment increases, no problem. If the unpaired electron increases also, you will get a different color will be formed from the complex ion. So today we have discussed about the magnetic behavior and the formation of a colored ion. Both the concepts similar. So from that magnetic moment, it is also we are talking about the number of unpaired electron. Formation of a colored ion also we are talking about the number of the unpaired electron. So magnetic behavior and the color will depends upon the number of the unpaired electron. Thank you.